We now take a look at introducing IPv6 networks as the next generation IP framework. With the gradual exhaustion of the IPv4 address space, new solutions for continued address space were needed. Temporary measures in the form of NAT were applied, however long-term solutions were required. The IPv6 addressing architecture is a developing solution for IP to provide for the next generation of networks and beyond. The transition to an all IPv6 architecture, while progressive, requires a major overhaul of many protocols and applications, as well as standards. The IPv6 network, however, aims to solve many limitations within the current TCP/IP suite, most notably addressing the need for integrated security measures and the streamlining of protocols to minimize overhead. A deep knowledge of the IPv6 architecture is required by engineers as IPv6 continues to evolve as an integral part of the enterprise network. Upon completion of this section, it is generally expected that trainees will be able to explain the characteristics of IPv6, explain the IPv6 addressing format and addressing types, as well as describe the process for IPv6 stateless address auto-configuration. With the continued expansion of IP networks globally and new networks being formed every day, the existing IPv4 addressing scheme is bearing a lot of pressure to maintain an adequate number of addresses to support this continued growth. As has been highlighted, temporary solutions in the form of network address translation and classless interdomain routing have aided greatly in suppressing the imminent exhaustion of the IPv4 address space in the short term. However, in terms of address availability, IPv4 has already reached the end of the line. Its successor is IPv6, which, as we see from the information displayed, involves transitioning from the use of a 32-bit addressing scheme to one that supports addresses of 128 bits in size. Through this transition, the addressing scheme provides an expansion of addresses from the original near 4.3 billion addresses of IPv4 to an unimaginable number of over 340 undercillion addresses that is expected to not only last for many years to come, but also open up a greater number of possibilities for IP networks in general. With IPv4 representing a huge foundation for many protocols, there lies ahead a major task of allowing these standards to support IPv6, which in many cases involves the redesigning of many standards. It will take a number of years for both IPv6 and supporting standards to be put in place. However, with the continued transition towards fully compliant IPv6 networks, it is important to be familiar with the implementation of the technology and supporting protocols. In terms of variation between both IPv4 and IPv6, we need only look initially at the IP header format for IPv6 to notice that the entire IP header has undergone something of a transformation in order to both support the new addressing scheme and also to streamline operations supported by IP packets. We find the version field remains in order to distinguish the packet header as being an IPv6 packet. The original type of service field that was renamed as the traffic class field in IPv4 continues to be supported in IPv6 for supporting prioritization of traffic, such as that originated from voice and video streams. The flow label represents an improvement to IP that helps maintain packet order over the network, to minimize the need for resequencing of packets at the destination, and thereby improve efficiency of packet flow. The protocol field is renamed as the next header, to standardize the terminology for referencing the next set of protocol instructions to be processed, and supports what are known as extension headers that allow additional functions to be supported by the IPv6 packet. The TTL field is also now known as the hop limit. Many other fields have now been removed, most notably the identifier, flags, and fragment offset fields, since these need not be carried in every IP header, except where fragmentation is to occur. As such, these fields are now carried as one of a number of extension header fields for IPv6. We show here how fragmentation is thereby supported in the form of an extension header where fragmentation is necessary. The fragment header is referenced through the next header field of the IPv6 header and will be processed accordingly where used. We find the same identification, flags, which is now set as the M bit to reflect that more fragments are expected, and fragment offset fields are present, along with additional fields for future expansion. The extension headers also include a next header field that will reference the next set of instructions to be processed, that we demonstrate here through reference to the TCP protocol header. There are in fact a number of extension headers that are implemented in sequence order, with examples included in addition to the fragmentation header that we see here, extensions for supporting authentication and encryption through the authentication header, and encapsulating security payload that were introduced as a component of the IPsec VPN framework. When working with IPv6 addresses, we will find that there are a number of differences to IPv4 that have come about in part due to the 128-bit size of the new address structure, but also as a result of a number of changes that attempt to improve the original IPv4 addressing scheme. The IPv6 address, due to its size, is commonly expressed through hexadecimal format, meaning that each cluster of 4 hexadecimal values represents 16 bits in binary. We can see an example here of how an address beginning 2001 would be represented in binary, with each set of 4 bits representing values between 0 and 15, which gives us our hexadecimal range of 0 through to F. The address itself may be comprised at a basic level of an address prefix, which is roughly the network portion of the address, while the remaining addressing space supports the interface ID range, or range for host address assignment. The prefix itself, though, may include more than just address ranges for the network. As we saw with the inclusion of subnet addressing in IPv4, IPv6 may also support additional forms of addressing that support a greater level of hierarchy within the IPv6 address space, including support for regional specific prefixes that cluster addresses based roughly on location, such as North America, Latin America, Europe, Africa, and Asia Pacific regions. Due to the size of the address that is now supported, its written form even in hexadecimal is considered somewhat impractical for everyday use. Therefore, in order to simplify the address itself, IPv6 is designed to support address condensing. This is possible in part due to the structure, but also due to the fact that the address space is so large that for some considerable time, it is likely that a huge portion of the address will contain large strings of 0 values. Each 16-bit cluster in hexadecimal is separated by colon values, from which we are able to remove the leading zeros in each cluster. As a result, we end up with a smaller address space that represents the same information. We find in the case of other clusters, such as where the address hexadecimal string is 0db8, that by removing the leading zeros, the address is simplified to db8, and in the case of a string of zeros, only the trailing 0 remains. Where a string of 0 clusters also exists, we can use the double colon to represent this address string and simplify the address further. Importantly, however, this double colon can only be used once in order for it to be possible to restore the original address before the address condensing was performed. The address architecture is made up of such a large number of addresses that currently only a small fraction of the entire IPv6 address space has been allocated for use. The main portion of the currently used address space is found within what is the global unicast range that is represented by the prefix of 200::/3. This global unicast range represents the scope of addressing that is considered routable within the public network domain, which generally refers to routing over the internet. This also includes certain reserved address ranges, such as the 2001:0db8/32 range, which is often found used for documentation references, such as we use here. Special ranges also exist to support what is called linked local addressing, that performs the role of private addressing and a lot more. We can understand it to support stateless addressing that is used to support link layer forwarding, meaning that it can automatically be assigned where no DHCP server is used to provide IP addressing, or where addresses are not manually defined. As we will see, linked local addresses also play a major role where routing is concerned. Another big change to IP involves the removal of broadcast in IPv6, instead relying on multicast addressing and what is referred to as anycast addressing, which we shall take a look at in more detail shortly, but generally relies on the global unicast address range. The multicast address range in IPv6 is represented by the prefix of FF00::/8. Addresses that are not specified for whatever reason are represented by a /128 prefix containing a double colon, whereas the loopback diagnostic feature of IPv4 that uses the address 127.0.0.1 is represented as the reserved ::1/128 address in IPv6. In respect of the supported unicast range of IPv6, we can understand that this comprises mainly of the global unicast and also the linked local unicast ranges, while subtypes do exist, such as, for example, IPv6 addresses embedded with IPv4 addresses. We show here the typical format of the two main unicast addressing types. In terms of global unicast addressing, this is made up of a global routing prefix that supports distinction of the general global origins of the data and may also be used to filter data based on regions or even sites as part of access control list policies. Where the global routing prefix refers to a site that within itself may contain a cluster of other subnetworks or links, these links may be distinguished based on the subnet ID of the address. The remaining interface ID is used to identify individual interfaces on a link, for which assigned interface IDs must be unique for the associated subnet prefix. We give an example of a common global unicast address here based on the currently allocated 2000:/3 address range. Link local addressing, on the other hand, is distinguished by the address prefix of FE80::10, which is equivalent in binary to the first 10 bits of the address, as we see in this example. The link local address contains a 64-bit interface ID to uniquely represent the range of hosts to which it is supporting. The link local address provides communication between hosts in the scope of the broadcast domain to facilitate in part link layer communication, and as such will often be assigned to interfaces of end stations and other devices where link layer communication is required. Due to the size of the IPv6 address and the fact that 64 bits are currently more than enough for supporting link local addresses, a 54-bit portion of the address is maintained as 0. Again, we represent here a typical example of a link local address, which we shall look at the application of more so as we look into the implementation of IPv6 routing. Multicast addressing works in pretty much the same way as it does in IPv4, in which one or multiple interfaces associated with the address will listen for traffic with the multicast address listed as the destination address. However, we find that since the broadcast address is no longer present as of IPv6, the multicast address has been designated to take on some additional roles. The multicast address is identified by the FF00::8 prefix, which in binary represents the format we see given in this example, in which the first 8 bits of the address are set with a value of 1. The structure of the multicast address in IPv6, however, also contains a flags field and a scope field, as well as supporting a group ID. The flags field consists of 4 bits that are assigned to support a number of advanced multicast features, as well as dynamic allocation of multicast addresses, but for the most part we can understand this field to represent a value of 0 that reflects well-known multicast addresses that have been defined by IANA. The scope, however, represents the range to which a multicast address will cover, such as a single interface, as in loopback testing for multicast addressing, the scope of a broadcast domain that we now know as link local, a single site, multiple sites that belong to a single organization, or even globally. We show here instances of special multicast addresses that we may find present in most implementations of IPv6 to support the communication of information, in some respect filling the void left by broadcast addressing, as we shall see as part of the stateless auto-configuration process. The first is used to identify all IPv6 nodes within a given range, with the FF02::1 address supporting all node addresses, and FF02::2 supporting all router addresses. In both cases, this is within the link local scope, as determined by the 2 value in the FF02 portion of the address that relates to the scope. Anycast can be understood as a new feature of IPv6 that was sorely missing from IPv4, which is capable of supporting a great number of features, some of which we introduce here. Firstly, we should understand that Anycast addressing relies on the global unicast address range, and therefore is generally indistinguishable from global addresses. In terms of operation, however, Anycast addressing allows multiple interfaces that typically belong to different nodes to be assigned the same IP address. In doing so, packets that are destined for a given Anycast address will be forwarded to one of the interfaces associated with this address, which generally will be the nearest destination to the sender that supports this address. At any one time, there may be a given sender or initiator and multiple potential recipients known as responders. In terms of application, Anycast addressing is ideally suited to support applications such as DNS, in which the end station will commonly reference a primary DNS and a secondary DNS in case the primary DNS server fails. Through Anycast, however, multiple DNS servers can support the same address, to which the nearest DNS server will serve the host, and should one DNS server fail, the end station is still capable of discovering the next alternative DNS server without the need for referencing multiple DNS server addresses. Other examples of this include supporting multiple gateways based on a single gateway address that allows networks to balance traffic coming in and going out from an enterprise network and provide redundancy in the event that one of the gateways happens to fail. In terms of security, it may be used to alleviate attacks such as denial of service attacks by distributing heavy traffic among multiple servers or gateways that prevents service availability from being disrupted. With every upside, however, there are considerations that must be taken into account, such as where servers are required to be synchronized to support services. The sharing of information between servers may be subject to capture and manipulation if not secured properly. We also find, in contrast to IPv4, that IPv6 involves a great number of changes to the way that addresses are allocated to end stations. Typically within IPv4, an address is allocated automatically, either through DHCP or as a result of automatic private IP addressing that assigns a host address in the 169.254.0.0/16 range and verifies the address is unique through gratuitous ARP in order to basically support link layer forwarding. With IPv6, however, we have what is known as stateless address auto-configuration, or SLAC, that enables end stations to obtain IPv6 prefixes and assign interface IDs without dependence on DHCP services. In support of this, we find that there are two packet formats defined. The first is the router advertisement that is generated by the IPv6 enabled gateway in the network to periodically advertise network configuration parameters used to declare the existence of the router on the network to end stations and other routers. We show here the typical contents of a router advertisement, which in itself is an ICMP packet that is distinguished by the type value of 134 and includes information such as the address prefix that should be used for stateless address auto-configuration by end stations. We will notice also that the advertisement is sent to the all nodes multicast address for the link local scope through the FF02::1 address, to which all active end stations will accept packets destined for. Along with this, we see some of the typical data that is carried as part of the router advertisement. In some cases, however, an end station may become active on the network but await router advertisements by which to complete its assignment to the network. In order to speed up the receipt of an advertisement from the router, the end station may generate a router solicitation that is advertised using ICMP packet type 133 and destined for the all routers multicast address of FF02::2, on which the advertising router will be listening for traffic. While the router advertisements provide the mechanism for supporting network discovery on a link, the assignment of a unique IPv6 address relies on other mechanisms such as manual configuration, system software-defined allocation, or the more common method of generation through what is known as the IEEE 64-bit Extended Unique Identifier, or the EUI64 format for short. This works on the principle of adapting the unique MAC address of the interface to generate a unique IPv6 interface ID. One thing that we may notice, however, is that the MAC address is made up of a 48-bit value, while the interface ID of an IPv6 address is comprised of a 64-bit value. If we recall, the first 24 bits of the MAC address represent an organizationally unique identifier that is specific to a given vendor or company, which we can see represented here by the value of C. This also includes the universal local bit, which will be set to 0 generally to represent that the address is unique locally, while the G value is the group bit that distinguishes unicast and multicast MAC addresses. We find, however, that where EUI64 is applied to generate a unique 64-bit interface ID, an additional 16 bits are inserted between the OUI, that represents the first 24 bits, and the manufacturer-assigned extension identifier bits that are seen represented here by the value of E. This 16-bit value is made up of 2 octets and is written in the hexadecimal form of FFFE, for which the binary representation can be seen in the shown example. In terms of the universal local bit, however, we find that when EUI64 is applied, it will be set to a value of 1, which gives the address a global scope that is expected to support technology developed in the future, which can take advantage of such interface IDs. Prior to the assigning of the IPv6 address to the interface, however, we must also ensure that the address is truly unique. This is performed using another mechanism referred to as the duplicate address detection, or DAD. Address duplication in IPv4 relies on ARP to perform gratuitous ARP each time a new address is assigned, or or a new end station is established on the network. In IPv6, however, we find that ICMP is once again the mechanism that is used to support DAD, as with router solicitations and advertisements, mainly to allow the protocol to be more media independent than ARP, as well as make it possible to support IP security mechanisms if such mechanisms are required. Duplicate address detection works by taking what is the tentative address for the interface and creates a neighbor solicitation to query whether the address is currently in use. In order to do this, the interface must firstly associate with two multicast groups that we know as the all nodes multicast group of FF02::1 and a solicited node multicast group. This solicited node multicast address uses a prefix of FF02:0:0:0:1:FF00:104 and takes the last 24 bits of the 2001::1 tentative address, which in this case is 00:0001, and appends this to the /104 prefix to create the 128-bit solicited node multicast address group, which we can see shown here as the destination address of the neighbor solicitation. This neighbor solicitation is represented as ICMP type 135 and currently defines the source address using the unspecified address format of : The destination is set as the solicited node multicast address, to which the query is performed. If the address is in use, possibly due to manual configuration of the same address on another end station, a neighbor advertisement will be generated, again through ICMP, by the end station that received the neighbor solicitation using the FF02::1 all nodes multicast address to inform all nodes on the link that the address is in use. In summary for this section, and we just have a couple of questions here. The first asks, what is the smallest condensed IPv6 value possible for the address that we see here? Well, we are able to condense the address by firstly removing the leading zeros, and then using the double colon, we can further condense the string of zeros to give an address of 2001:DB8::32A:2D70. How is it possible for an end station to independently generate an IPv6 address? Well, through the use of HUAWEI64, we are able to generate a unique IPv6 address by inserting two octets in the hexadecimal form of FF and FE between the OUI and the unique extension identifier values of the MAC address to generate a unique 64-bit value to use as the interface ID of the IPv6 address. Duplicate address detection will then be used to validate that the address is truly unique.